Hello. I'm very pleased to be able to be here today and coming from halfway around the world to, I was asked by the organizers to kind of go back to my proof, which now is, if you go to the archive date, it was 2014, so it's 10 years ago. There's obviously been a lot of controversy in MBL, many different ideas. The field has developed, matured, and many doubts have been put out about whether there truly is a MBL phase in infinite volume. And the numerics, experiments, it's very difficult to extrapolate those to infinite volume. So when it comes down to the theoretical question of whether there is or is not a phase in infinite volume, it comes down to this proof. And but yet, at the same time, I think it's a bit of a mystery. People say, oh yeah, there's a proof, but how does it work? I mean, not too many people have actually read the article. It's a very technical article. So the goal for today and tomorrow is for me to kind of give an introduction to the ideas in the proof. Those of you who don't want to read the proof, but probably most of you, at least will get an understanding of what's behind it. And if there are some people who really want to delve into it, then this will be a good introduction to see what's going on with it. So the first lecture, can you put it back up? So in the first lecture, I'm actually not going to be talking about an MBL system. I'm going to be talking about a very familiar system, the Anderson model. And I'm going to show how these whole idea, but actually this was kind of a warm-up problem for me. I knew that I could never approach the MBL problem unless I understood the Anderson model in the proper way, in a way that would generalize to the many-body setup. And as it turns out, and if we go back to the archive dates, both these papers were 2014. Once I had solved the Anderson model in a way that was suitable for generalization to MBL, then it was a relatively short step to get the MBL theorem. So this first talk will be hopefully much easier to understand and follow. And okay, so here's the outline. We're going to introduce the Anderson model, talk about the resonance set, Schrieffer roof rotations, as I mentioned earlier, graphical analysis, and etc. We'll get to those. So here's the Anderson model, the simplest model that I could come up with. It's just unperturbed. The off-diagonal elements, this is basically a nearest neighbor hopping term, and then we have a diagonal disorder given by an operator J. The J is the hopping matrix. H0 is sort of the unperturbed energies, represent the random potentials at each site, delta x, y. So these are going to be IID, smooth distribution, the usual Anderson model. And the hopping then is just nearest neighbor hopping. And the whole idea behind this problem, and in fact the MBL problem, is it's basically perturbation theory off the diagonal. H near zero is the diagonal matrix consisting of all the potentials, and we assume that we have a large disorder, so the distribution is very wide. The potentials are most of the time very large, so it's a strongly diagonally dominant matrix. So it's the simplest possible regime to talk about Anderson localization. All right, but no matter how large the disorder is, we have to deal with a resonance set because, of course, there are resonances. What is a resonance? Well, I say you have a resonant pair if the potential at x and y differ by no more than epsilon, where this is a small power of J0. I should have mentioned that J0 is a small parameter. I'm just doing perturbation theory essentially in J0 whenever it's possible. And we just do this for nearest neighbors x and y, at least initially. Now, because the distribution of the potentials is very wide, or actually, I guess here we have a small parameter epsilon, so I don't have to take a wide distribution. Whatever the distribution is, if this neighborhood is made sufficiently small, which is governed by J0, which is also small, then the probability that the two potentials are within epsilon of one another obviously goes to 0 with epsilon. So this initial resonance set, S1, is a dilute subset of lambda. And we don't try to do the Schrieffer-Wolff rotations in S1, at least initially. We'll get to that in subsequent steps. Ultimately, what we have here is an RG procedure. And right now, I'm just talking about step 1 of the RG. So we want to define a rotation, the Schrieffer-Wolff rotation. And it's given by this matrix AXY, which is, here I call it the perturbative parts of the off-diagonal matrix JXY. That means it's JXY, but only for those X and Y that are outside of S1. Otherwise, it's 0. So I'm only going to perturb in those terms that I know are suitable for perturbation. I don't perturb with respect to anything large. That's a general philosophy in mathematical physics. Certainly in many of my work in mathematical physics, is never try to perturb unless you know what the answer is. Isn't that what lawyers say? Don't ask a question unless you know what the patient is going to, what the witness is going to say. So I don't perturb unless I know I have a good perturbation theory. You just kind of pulled out of a hat. I wanted to have a small number, yeah. Yeah. Okay, so let's go to the next slide. So this is a slide on the Schrieffer-Wolff rotations. The key point here is that the reason for defining this A matrix, this generator, as we've done here, is it has the property that when you commute it with the Hamiltonian, you get negative J per, negative the term that you're trying to get rid of, right? I'm trying to get rid of these terms. Basically, I want to, initially, all the terms in the Hamiltonian are of order J0. When I'm done, I want all the terms in the Hamiltonian to be of order J0 squared. So we're trying to get rid of those terms, but of course there are corrections given by these commutators. And so if you do these rotations on the matrix A, you get a whole series. You initially have H0 plus H res plus J per, but then you get a minus J per from this and these commutators. And you can rewrite this series, I won't go through the details, as a sum of these terms, basically powers of A and J. Now remember, A is basically formed out of J with that energy denominator, so it's basically also of order J0. Question? Yeah, this is a convergent series provided you have, that these terms are bounded, which they are. That's part of the purpose of putting in this. I'm only doing it for the non-resonant sites. So I have an explicit upper and lower bound on the size of the matrix A. Not lower bound, but I have explicit upper bound. The size of the matrix A is basically of order J0 to the 19/20th. Okay, so these adds are basically the commutator. All right, so what does this mean then? Let's think about this graphically. What happens when, let me just go back for a second. When you do this commutator, add A applied to J, or even the first term, commutator of A and J, you have terms in this commutator AJ and JA. These are matrices, and obviously the indices have to match up. We're used to thinking of J as generating a random walk because its nearest neighbor steps in the lattice, but also the matrix A being based on J, right? J is basically J with just energy denominator thrown in. It also generates walks in the lattice. And so when I look at various terms in this expansion, first of all, I have these dark lines which represent individual steps in the lattice. So this is the fundamental graphical picture. But on top of that, we have all the energy denominators coming from here. And so I like to draw those energy denominators with arches. And if we have an expansion for an A matrix, the number of arches matches the number of steps in the lattice. If we have a J matrix, we're short one arch, because again, we have this term here like with just one A and one J, let's say. The A has an arch, the J doesn't. But it's a relatively minor difference between the two expansions. What that means is we can bound this graph, which I'm basically, this graph I'm going to call it by a letter G1, because it's in the first step. And the associated term in the rotated Hamiltonian I call J1 of G1. And this is bounded by, basically, we have one short denominator, right? So we have J0 over epsilon to the G1 minus 1, the size of the graph minus 1, and then one extra power of J. The net result here you see is that this is essentially of order J squared as claimed, but now you see why I took epsilon to be very small. It's actually slightly short of J0 squared by a power of 1/20th. That's why I wanted that to be a small power. All right, so this then basically converts what initially was a nearest neighbor step in a Hamiltonian to now we have long-range steps. Although if I go from here to there, I'm going to have exponential decay because I have to take, if I have from x to y, the distance from x to y, that equates to the minimum number of steps I need to get from x to y, which translates to a high order in this expansion. So these graphs decay exponentially, and this is not a probabilistic statement, right? As long as I'm talking about these non-resonant graphs constructed from these Schrieffer-Roof rotations, it is, by definition, all these graphs obey the bounds that I've essentially put in. Of course, there has to be a parallel analysis. If I'm going to assume certain bounds on objects, I need at the same time to talk about the probability that those bounds are violated. And that's the fundamental duality that you'll see throughout these lectures. You have uniform bounds, which are true all the time, but then you have a probability bound on the probability that those bounds are violated. So we have exponential bounds uniformly where we have them, and we also want to have exponential bounds on the probability that those bounds are violated. That's the key duality throughout today's proof, and similarly when I get to the MBL problem tomorrow. Okay, so that's basically the perturbation theory. It's not hard at all in the Anderson model context. Now we need to talk a little bit about those regions where we didn't do these Schrieffer-Wolf rotations. Sometimes I call these resonant blocks or just blocks. So what we do is we kind of expand the initial resonance set by including its first neighbor. And later on, this collar neighborhood, if you will, is going to become larger. But initially, we just add one site, and we divide its component into small and large blocks. So these blocks, you see, have a scale unto themselves. Basically, their diameter gives you a scale. And so when we do these probability bounds, they have an RG character as well. They're going to be done step by step. We can't do rotations in extremely large blocks just yet. What we can do are rotations in the smaller blocks. So anyway, here are those small blocks, and here are some large blocks. And we have some connectivity basically coming because of the fact I took these first neighbors. We have some connections as well. When we get to subsequent steps, instead of 2 to the 2/3, it's going to be LK to the 2/3. So now here we've introduced a series of length scales, LK, which is 15/8 to the K. You can see this is almost 2 to the K. And really the difference between this and 2 to the K has something to do with that 1/20th that you asked me about earlier. Because as you know, as I indicated a moment ago, the first non-trivial term in the expansion has uniform bounds which are J0 to the 1 plus 1920. So it's not quite squared. This is basically a Newton's method kind of operation. And so we're going to be slightly off from quadratic convergence. If we were doing quadratic convergence as in Newton's method, the traditional Newton's method, this would just be 2 to the K. Well, yeah, I just explained, actually. I kind of pulled 1/20 out of a hat, just a pretty small number. And once you do that, then this number has to differ from 2 by more than 1/20th. In fact, it differs by 1/8, so we're in good shape. Yeah, this number had better be bigger than 1. You definitely need super convergent, and I don't know, just aesthetically, I thought it was better to keep it close to the quadratic convergence rather than somewhere in between linear convergence and quadratic convergence. So that's why we have some of these. And I mean, as far as making the paper easy to understand, I think it's easier to work with specific numbers rather than, sometimes in mathematical papers this could be like 1 minus eta or something like that. And then pretty soon you start reading and you have all these different Greek letters and you don't know what they are, which one came first. And so keeping them fixed is a way of making the relationships between them more understandable. But yeah, thank you for that question. Of course, all of our speakers will say this, but specifically because I'm trying to make this a pedagogical lecture, I really do hope that if you have a question, you are emboldened to ask. Okay, so so here it is. I have to cap the volume of these resonant blocks by and again, this 2/3 is some number, which it really just has to be something less than 1. The idea is that the exponential decay, which is going like J0 over epsilon to the LK, has to be much smaller and keep this under control with room to spare. And obviously, this is an exponential of LK to the 2/3. This is an exponential of LK to the 1 power. So this is definitely going to be much smaller than that. And it will ensure that the sum over states in the block will be kept under control. Now, one of the interesting things about this procedure is that you have certain interactions here between these blocks and this immediate neighborhood. Remember I said that width of this neighborhood is basically LK. So if you have an interaction diagram which is of order smaller than LK, it can't possibly reach to the exterior of this neighborhood. At the same time, these residual interaction terms are not small enough to be treated perturbatively. Although individually they're small, the number of them is so large that, yeah, this was kind of a stumbling block for me for a long time. I kept thinking, surely there must be a way to perturb away these diagrams, but there's not. And ultimately, as I say here, it's connected to the thermalization of collar neighborhoods of resonant regions. So as we see in this effect, it gets much, much stronger in the MBL case, where if you have some resonant region, you have to back off from it considerable distance before you can start to treat interactions perturbatively. Basically, you have two exponentials in play. One is the decay of the interactions, and the other is the growth in the number of states. And it may take some while before one exponential beats out over the other one, requiring a collar neighborhood. But even in the one-body problem, which I'm considering today, you have collar neighborhoods, and they're much less significant in terms of how they affect the proof, but they definitely have to be kept track of. But again, it's good to see this in this more limited context before we progress tomorrow to the MBL proof. Okay, so when we do the graphical analysis, as I hinted at earlier, we use a sequence of length scales. And in each step, we rotate interactions that are lower order than J0 to the LK. So this is a kind of Newton's method, slightly slower than quadratic convergence. But you see, as a function of K, these the residual interactions are being driven to zero extremely rapidly, much more rapidly than an exponential in K. It's a double exponential in K, in fact. So this is Newton's method. It's if a term of order LK is rotated away, it creates new terms of order 2LK or more. Right, remember, these rotations, let me go back to the earlier slide here. I'm doing this formula basically for my rotations, and the linear terms disappear, and we're left here with these terms like AJ, which are quadratic in J0, plus some energy denominators. Okay, so now I need to get into the question of, remember I said that, I guess you never started this. You'll just have to yell at me, whatever, but I didn't want to keep a rough idea of how much time I have. I'm about halfway through, I guess. So remember last time, or earlier today, I said that we have sort of uniform bounds in certain areas, but then we have to use probabilistic bounds to talk about the probability that these uniform bounds fail. Okay. So there, this is a picture of a graph. If it's an interaction term, we'll be missing one of these arches. But let's talk about these A matrices. These are the matrices which generate the rotations, right? So it's really important that when we try to do a rotation, that we have good bounds on the rotation generator. Remember, basically I'm talking about L infinity bounds, uniform bounds. I want to know that these rotation generator satisfy a bound analogous to the one I assumed in the first step. So I'm going to say that a graph, it's basically a graph by graph analysis. A graph of order LK is said to be resonant if two conditions hold. Firstly, this rotation generator is larger in magnitude than I would like it to be. And actually, I put in here gamma. I should have said J0 over epsilon. I'm mixing up the two proofs. I'm using gamma, I guess, in the MBL proof, but in this proof, it's J0. Anyway, with that modification, you can see this is a natural generalization of what we did in the very first step, where we said a large set is defined by a situation where the A matrix was, or the matrix element of A was larger than J0 over epsilon. But now that we're doing larger graphs, we have a similar measure in term based on the size of the graph. So what this means then is if it's larger in magnitude, then it has to be considered a resonant graph. We can't perturb with things that are not small enough to perturb with respect to. You don't ask a question of a witness unless you know what he's going to respond. But then there's a second condition, which is a little bit more technical, but it's a key aspect of the proof. First of all, I have to define a metric in space with a superscript J. This is a metric where blocks on scales up through J are contracted to points. So the idea is that you have exponential decay going along. Merrily we roll along, we have exponential decay, but then we hit a block. And it's kind of like a short circuit in electrical networks. There's going to be no exponential decay through this block. And then if we continue, we get exponential decay in these areas, but not across here. This also plays a key role in the MBL context and even in the theory of the transition, this idea of these short circuits, which have a tendency to interrupt exponential decay and actually reduce the rate of exponential decay that you're able to demonstrate. So what I'm doing here is I'm saying that there is not very many of these intermediate holes, if you will, or gaps in decay. The metric between x and y, the metric distance between x and y is at least 7/8 of the length of the graph. So clearly, if you have a graph and it goes absolutely straight, right? The maximum distance for a straight graph would be the modulus of g equals x minus y. But if we have some excursions along the way, then this distance between x and y is going to be a little bit smaller than this length of the graph, clearly, right? So what we're saying here is that these graphs are very close to being straight because they achieve very nearly the maximum distance between x and y that they can, given the length of the graph g. No, the length of the graph is simply the number of steps. And so when a graph hits a resonant region, that's just one step, and then one step out. So that's a good point. Length of g is the number of steps. So, but you'll notice that I put in this modified metric distance. So the fact that it stepped into one of these resonant regions doesn't hurt it as far as this estimate is concerned, because that's not counted in this notion of the metric distance between x and y. Okay, and so yeah, I'll explain exactly why this is done this way, but it's the key technical issue that I need to straighten out in the one-body context in order to get a uniform procedure and then to move on to the NBL context. Yeah. No, they can cross, yeah. It's basically, it's nothing fancy about this graph. It's basically just the graph you get by multiplying matrices. The indices are x and y, so when you multiply matrices, every term in the matrix multiplication corresponds to some kind of a walk in space. Well, yeah, this very clearly, this is the whole point is, yeah, the forward approximation. In the forward approximation, you assume that every step in the expansion introduces a new site and a fresh random variable. It's all very well to work in the forward approximation. It certainly simplifies many things. And, you know, of course, in proofs of even Anderson localization go from being, let's say, I don't know, 20 pages to 2 pages if you assume the forward approximation. So yeah, but in the mathematical work, we have to consider all the graphs, and so this is basically a construction that I devised to deal with that. So yeah, very good question. Okay, so what we're going to do then is use what are sometimes called fractional moment bounds to control the probability of a resonant graph. So if I take this rotation generator, AXYG, this is, because of this energy denominator, I can't take it to the 1 power. I have to take it to a power s less than 1. I should have put that in this slide, but so it's a fractional moment. So s has to be, and there's some, I think I choose 2/7, or anyway, I choose some fraction. Doesn't much matter, but clearly if you're going to do this integral with respect to the v's, the power in the denominator has to be smaller than 1. And this also is the key aspect of why if you have a graph which returns to the same spot, then you're going to have a bunch of energy denominators. Well, in the simplest case, maybe you would go like this. Right, so this energy denominator would appear twice, right? But then that means instead of x minus y to the, let's say, 3/4, it would be x minus vi minus vj to the 3/2 if it appeared twice, right? Well, obviously then that's disaster. You can't integrate 1 over v1 minus v2 to the 3/2. So this is, in terms of probability estimates, we see how it's important to stay away from those places where you get repeated, basically graph returns to where it was before. So as I said, this assumes every side is different, which is also known as the forward approximation. But let me come back to this before I talk about how we deal with those problematic areas. What we have here is that the fractional moment of A is bounded by an exponential in G, if this whole thing is working properly. And then you have Markov inequality, which says the probability that this is bigger than some exponential is itself an exponentially small probability. And that's the key aspect of this construction, which is why I needed to develop new techniques in the single body problem, was to essentially to get exponential bounds on probabilities, which in most of the, I'll talk about this at the end of the lecture, but the traditional proofs using multi-scale analysis, of which this is, get at most stretched exponential decay of probabilities, which because in MBL, the state sums go exponential with the size of the region, we can't have stretched exponential decay. We have to have true exponential decay. Okay, so now let's talk a little bit about the backtracking or return to previous sites. If we have significant backtracking, that is coming back to here, this inequality here defines the boundary between little backtracking and lots of backtracking. So graphs that obey this inequality have very little backtracking. And so basically, if you look what I said here, we say it's resonant if both these conditions hold. That means I'm not trying to make a statement about the probability of a resonant graph, except for largely forward graphs. So how are we going to deal with those graphs which are not largely forward? That's and this slide here is the answer to that question. If there is significant backtracking, we don't use the Markov inequality. Instead, we get extra decay compared with x minus y. So a walk with repeated sites, as we saw here. Once you start going side to side, or if you come back to where you were, obviously you can't get as far. So what I care about then for these, basically I'm going to sum over all these long graphs that have many backtracks, but they're all going to have extra exponential decay compared to the leading terms. So they're going to behave like some j0 to a power of x minus y, but that power is going to be greater than what I'm proving for the straight graphs using the Markov inequality. And that extra decay gives me a little wiggle room in the proof to essentially say that these graphs are really not going to mess things up. So anyway, when you have a bound on the probability of a resonant graph, which is exponential in LK, that is, which is also the number of graphs of that order, then we can define a percolation problem, which essentially, let me go over here. Now I'm going to talk about the percolation problem. This percolation problem was very simple in the first step because we had bonds were resonant if the VI or a site was resonant if it was basically if there was part of a resonant bond, and the resonant bonds were very simply defined. We basically had bond percolation. And the clusters were just the clusters of bond percolation, the bonds being those resonant bonds. That's all very simple. But now in the general step, we have these graphs, which I can sort of draw schematically like this. And all these resonant graphs, if we combine them, they also form a percolation cluster. And I need to understand, basically, I need that the percolation conductivity function for all these resonant graphs decays exponentially. Now, as long as the individual probabilities of these graphs is exponentially small, I think you can see that you can sort of combine these exponential decays, and at the end of the day, you're going to get a conductivity function for the percolation cluster between x and y is going to decay exponentially. So that's telling us that these resonant clusters, although they're complicated in structure, but at the end of the day, they form percolation clusters, which are nice, probabilistically speaking, like if you're in the non-percolating regime, they're not very big. Their conductivity function decays exponentially. All right, now let me return to these backtracking graphs. And I guess I said some of this in words already, but basically, we can think of this as a kind of like a timeline of the walk. All right, so here horizontally, the axis is the time of the step number, if you will, of the walk, which is describing some kind of walk in space. And then we can graphically denote the situation where the walk returns to an earlier visited point by an arch. So an arch here indicates that at this time, the walk returned to the site it was at this time. And you can have more complicated structures where it goes from here to there, and then comes back here, and then goes back there. And you can have graphs inside. But at the end of the day, what you see in all these situations is a kind of multiple connectivity. Now I'm going to return to physical space. Down here, I'm doing physical space. The walk is going to a site, goes to another site, returns to the first site, then it goes to the other site, and it goes along its merry way. Well, clearly, there's a lot of wasted steps in this process in the comparison between the length of the graph and the actual distance between x and y, right? That's what I mean by multiple connectivity. So that gives us lots of extra exponential decay to work with. Using bounds from the previous step, we know that every step of this walk exhibits exponential decay. And so this extra wiggle room in decay is what I alluded to earlier when I talked about the fact that we didn't need to do probabilistic bounds for these long walks. And the fact that you need extra decay, if this were just marginal situation where the amount of decay was just x minus y, that wouldn't be sufficient. You need, in all these mathematical constructions, you need some wiggle room to, if nothing else, to sum over scales and things like that. Anyway, so I hope this gives you a flavor for how we deal with these corrections to the forward approximation. So now let me go on to the actual theorem, again in the one-body context. This is a kind of a straightforward statement of Anderson localization, stated from the point of view of what's called the eigenfunction correlator, where you sum over the eigenfunctions of psi x, psi y. So clearly, if you have an eigenfunction which has some localization center and it decays away from that, if you're going to go from x to y, you have to basically first go to the localization center and then go to y. And since both of these progressions involve an exponential decay, ultimately you get a decay from x to y. And so we have a positive kappa, which gives us a rate of exponential decay as a power of J0 on this eigenfunction correlator with an expectation on the outside. And consequently, again, using Markov's inequality, if you want to know about a specific event, what is the probability that that this eigenfunction correlator is smaller than this exponential? It's going to be 1 minus an exponentially small number. So this is the key aspect that I alluded to at the beginning. I need to have exponential bounds on probabilities. If I turn this around, the probability that this is too big is going to be bounded by J0 to this kappa x minus y over 2. So the probability that the eigenfunction correlator isn't doing what you want it to do is also exponentially small in x minus y. And in terms of how do we actually get this, well, in the course of the proof, you know, this is a multi-scale process, but at every step we generate these rotation matrices. So the actual eigenfunctions are simply a concatenation of all those rotation matrices. And once again, you know, when you multiply matrices, each term in the matrix is a graph. You multiply them, the graphs concatenate. So when we do this, we essentially produce a graph going from x to y. These graphs exhibit exponential bounds in the number of steps, but of course then there are these regions here where you don't get exponential decay, right? But under the expectation value, inside of this little box here, we have a structure like this, where we have all these resonant graphs. And under the expectation value, we get exponential decay there as well. So at the end of the day, when you're doing this expectation value, you're able to draw upon the exponential decay, sort of the L infinity, the uniform decay here, and then the probabilistic exponential decay for the resonant regions. And together, they combine to produce this exponential decay. Okay, so let me conclude this discussion by reiterating that this is basically a warm-up exercises for the MBL problem. And so I'm going to defer to, obviously, to next lecture, how these ideas need to be adapted in the MBL proof. But let me just reiterate what I've said earlier, that what I need to address in this paper, this 2014 paper on the Anderson model, was the lack of exponential bounds in multi-scale analysis proofs of localization. You know, the mathematical literature on localization, Anderson localization, is really extensive. It is a major field of study, and it goes back really to the early work of Froelich and Spencer. 1983, I think, was the first rigorous proof of Anderson localization. So there's a lot of multi-scale analysis work, but then none of these MSA proofs were able to give exponential decay. They gave at best stretched exponential. But that's not going to be good enough to control the exponential state sums in the MBL problem. Now, this theorem here is actually not a new theorem, essentially. Maybe it hasn't been stated exactly like this. because it was proved by the fractional moment method of Eisenman-Molchanov. But that was not a multi-scale analysis problem. That was not an RG analysis, and so there did not seem to be any possibility of adapting that idea to the NBL problem. That's why I had to devise this, basically redo Anderson localization in this suitable method. Now, of course, the idea of fractional moments did play a role. As remember, when I did the Markov inequality, I had to take a fractional moment, so those denominators had a power less than 1, and you could control the integrals over the v's. So there's maybe some echo of the fractional moment method present in what I did, but fundamentally it was a new construction. Okay, so I think that concludes today's talk, and I'd be happy to take further questions.
Okay, questions? Yeah.
So in the statement of the theorem that you had like, you know, there is some small enough J naught, there is a kappa. How explicit can you be about like the bounds on like how small is small enough for J naught? How large can kappa be?
Yeah, not very explicit. I mean, it's the nature of these types of proofs when you say something is true for sufficiently small parameter that in most cases you don't put a lot of effort into trying to, certainly in none of my papers have I ever tried to figure out how small is small. And partly because if you really wanted to do something quantitative and saying, well, J0 less than, let's say, I don't know, 1/100 would be good enough, it would just make the whole proof that much longer as you try to keep track of all these constants, and it would interfere with readability. Readability is already enough of a problem that it's really better not to try to address the question of how small is small. If you really went through the numbers, I'm sure it would be a rather discouraging number, and even more so for the NBL proof. But ultimately, when it comes down to establishing the existence of a phase, whether it's 10 to the minus 2 or 10 to the minus 9 or whatever, the phase exists. And then it's up to some other analysis to attempt to discover where the phase ends.
Do you think that like this method would be sufficient to see that, for instance, like, you know, J naught can be anything in 1D or 2D?
Oh, no. This is a I mean, a much better method, certainly in 1 dimension, which would be, I mean, this method would work, obviously, for 1 and 2 dimensions, but it doesn't going to give you very good numbers. And once if you say you want to know localization for all values of J0, well, clearly this is not going to be the proof you'd want because this is a perturbative. Theory requires small J0.
Okay, thanks.
Okay, yeah.
Yeah, so, yeah, maybe I kind of jumped over that. So it begins with this bound on the moment, the fractional moment of this rotation generator. We see that fractional moment exhibits exponential decay in the length of the graph. So then if you do Markov inequality, maybe I should repeat the question because I guess you didn't have a mic. Is that right? Anyway, but let me repeat the question. The question was, how do I actually get exponential decay of the probability that a graph is resonant? And the answer is to use Markov's inequality. In the Markov's inequality, you have bound on an expectation, and here's the bound. And then the probability that the random variable in question is bigger than b, let's say, is bounded by the expectation divided by b. That's Markov's inequality, right? Maybe I should write that. It's always hard to... somebody speaks out an equation, usually doesn't make much sense. Expectation of x over b, the probability that x is bigger than b, let me just put absolute values here, bounded by the expectation over b. Since the expectation exhibits exponential decay, I can say I can choose a slightly different exponential decay rate for this b, and then the probability that x fails to decay exponentially is itself going to be bounded by an exponential.
Okay. Yeah, question.
For a many-body system, is there a way to see why this A matrix is bounded?
Well, I'll get to the many-body situation tomorrow, but you have a very analogous graphical expansion that I'll develop tomorrow involving spin flips in the model that I work with for MBL. And since you have, the graphical expansion involves commutators, right? Go back to the beginning here. The graphical expansion is based on commutators. So when you talk about a rotation generator involving a spin flip here and a spin flip there, they're going to commute, except if they're basically next door to one another. Yes. And so then if you keep doing more spin flips, you end up generating a graph, which of course is, in some sense, it's a graph in spin configuration space of a transition involving multiple steps in spin space. But then this projects down to the physical space because of this condition that these rotations, they have to be right on top of one another, otherwise the commutator will be zero. So at the end of the day, you actually do get a graph in physical space as well as a graph, a connected graph in spin configuration space.
Okay, thank you.
Okay, any other questions? Let me then ask the final question. So could you remind us here, where does the lattice dimensionality enter?
Well, you talk in this Anderson model problem or in the next?
No, in this one.
Yeah. Yeah, the proof that works for any dimension. Yeah. I mean, I guess, you know, I'm not saying it would be uniform with respect to dimension because the counting of graphs depends upon the dimension, but the fact that you have exponential decay in every dimension follows from this.
How about infinite dimensions?
Well, yeah, I haven't really thought about infinite dimensions, but yeah, I wouldn't say it applies to infinite dimensions. Yeah.
Why not? Like, what about the proof would fail for like an arbitrary graph?
Well, you know, I mean, you have, whenever you go to infinite dimensions, you have to take a suitable limit. And if you just naively went to infinite dimensions, there would be infinitely many possibilities for each nearest neighbor step, right? And so I can't even define what it means to have a graph very straightforwardly in infinite dimensions. Yeah.
But I mean, okay, what about like some like model of like regular random graphs or something? Something where you like you have bounded connectivity, but like no notion of like dimension.
Yeah, okay, yeah. Well, so if you had bound, yeah, to be honest, I haven't really thought about RRGs, things like that. So I can't give a very well-informed answer to your question. But certainly there would have to be new ideas. I mean, RRGs are often thought of as like an approximation to the MBL problem, which is supposed to be simpler. But as we'll see tomorrow in the MBL problem, the physical space plays a very important role in my proof. You have to define notions of blocks and these neighborhoods, the neighborhoods which get thermalized. And all this is done in physical space, as well as the, so you get a benefit from that. And another thing is you have a rotation matrix, which involves the effect of a given spin flip. Well, in principle, rotation matrix is, in 2 to the n by 2 to the n matrix. But you have essentially locality. It acts trivially on all those other spins, and it only acts on a small subset of spins. So I'm constantly using in the proof this notion of locality, which I suppose is absent when you talk about localization in Fock space or on the RRG. And so I don't have any very well-informed comments about how to handle those cases.
Okay. If there are no further questions, then let's thank John again.